let's get started. First speaker is Ryan. Go ahead.
Oh, do I start now?
Yeah.
All right. Hello, everyone. Today I'm going to give a half talk, half rambling about some stuff I've been doing in Liquid Haskell. In particular, how it relates to type classes in Haskell. So, first, as a quick refresher, Liquid Haskell is an extension to the Glasgow Haskell Compiler that gives you refinement types. So here's some syntax you might write in Liquid Haskell to give a refinement type for a function. So this says that divide is a function which takes an int and another int as an argument, and the second int has this refinement type that must not be equal to 0. So with this, you can write a division function that ensures that you never divide by 0. Another thing that Liquid Haskell lets you do more recently is refinement reflection. So not only can you give refinement types, but you can also lift entire Haskell functions into the logic that Liquid Haskell reasons about. So as one example, you can take this Fibonacci function, you can reflect it into the logic that it works on, and then you can prove things about it. Like in Fib1, we can show us a really simple example of proof that Fib1 in fact equals 1, and we can verify this at the type level, and we've got some like proof combinators that let you pretend like you're working in a proof assistant. So one thing that we've been pondering in the project that we've been working on is it possible to take refinement reflection and also give it the power to work over type classes? So as one motivating example, if we have like a semigroup class with some binary operation, which I will call append, which is for shorthand, we might want to be able to verify that this operation is associative. So we might want to have some kind of verified semigroup class, which uses Liquid Haskell to express a property that given 3 values of type A, you can reassociate the order in which you append them, and that should just work out. Oh, sorry, did you have a question? Yeah, please stop.
Saying the what's the difference between single and double colon here?
There's not really an especially important difference. Technically, like this is not legal Haskell syntax. It's kind of a hybrid Haskell and Liquid Haskell type signature. So they use single colons in Liquid Haskell for reasons I don't fully understand. Like you would think they would keep the double colon convention, but
so this is pseudocode.
This is, yeah. If you're actually writing Liquid Haskell, or sorry, yeah. If you were actually putting Liquid Haskell inside your files, you would like write this type signature without the extra like X, Y, Z and this brace syntax, and then you would write this extra stuff below that in a special comment syntax. So like, I kind of did this earlier. We have the special comment syntax that Liquid Haskell sees. Like, you would write that refinement type signature within that. But to save space, I decided to just combine it all into a single slide. So this is the kind of thing that we want to do, but unfortunately, it's not currently possible for the time being. So one question is, why hasn't this been implemented yet? One reason is no one's had time to do it, but a more interesting reason is there's a bit of an impedance mismatch when you actually think about what code people write with type classes involved and what code GHC actually sees when you compile it down. So to better explain what I'm talking about, let's revisit the semigroup example. So this is what you write in the surface syntax in Haskell. When you pass it to GHC, it's going to compile this and turn it into GHC core. So I will use this light blue color to represent GHC core. So in GHC core, type classes desugared out into actual data types, or dictionaries is what we would probably call it. So instead of calling a class, we would just actually pretend that this thing is a real data type with some field named append. Now, if you were to write an instance of semigroup or something, I'll just pick the unit type, which has one constructor called unit. Then in GHC core, this would look something like this. So you would create a top-level binding for this append function for units, and then you would create a dictionary value, which I'll just call semigroup unit to give it a name, and then that would be the implementation of it. So as one more example, if you have a function which takes as a prerequisite that some type has to have a semigroup instance, in the surface syntax, this semigroup A thing here is not a visible argument. So when I write this out, this looks like it only takes 2 arguments because the semigroup A thing here is implicit. But when we compile down to GC core, it becomes explicit. So now we have an actual extra argument corresponding to this semigroup dictionary. So we have to explicitly pass it around, and then when we call append, we have to grab the append implementation from that dictionary in order to use it. So, okay, back to refinement types. What does this have to do with anything? Well, it turns out people are going to be writing refinements over things involving dictionaries, but there's a bit of a trickiness here because Liquid Haskell internally operates on GZ core, but the refinement types you write are expressed using something closer to surface syntax. So we have to find some way to translate the former to the latter. So in other words, any refinement type you write has to be able to survive being compiled to core. So how can we do this? Well, one crazy idea I had was just, well, if we are really compiling type classes down into dictionaries, that is data types or fields, let's just put refinement types on the fields. So have something like this, right? We can just say, okay, well, the append soak of this verified semigroup dictionary has a refinement type like that. And that almost works, but there's a problem. We have this, oops, that didn't quite render the way I wanted to, but there's, these D things here are not bound anywhere. They're just floating. I was kind of hoping that there would be some dictionary in scope, but we never bind it. Like the thing I really want to pass here is like the verified semigroup dictionary itself, but there's not really a clean way to express that. It's this weird circularity going on. So I guess what I kind of want to say is like for any verified semigroup dictionary D, then this should hold. But sadly, it's not quite possible to write that, and it's due to unfortunate technical reasons. Liquid Haskell works in a logic that is quantifier free. So trying to write for all D here inside of a refinement type is just a no-go because when we actually pass these refinement types into like an SMT solver like Z3, we're not allowed to express these sorts of types because it doesn't have the level of quantification needed to express it. So we're stuck there, so we need a different approach. So maybe instead of just trying to refine the fields of a dictionary, we should try to make refinement typing rules where we give properties to the actual instances that we write. So if we have verified semigroup again, then we can write an instance for unit. And then when we compile this to GZ core, this is going to look something like this, right? We have this top-level binding for this dictionary. And moreover, we can generate a typing rule for it. So if we see any occurrence of appendisoc where the first argument is this dictionary, then we know that it has this refinement type. So this part is pretty much just copy-pasted from the class refinement type here. And then moreover, like you have to reflect its definition. So I omitted it for brevity, but you're going to have some sort of implementation for append here, and then you're going to have to copy-paste that into here. So it's not the cleanest solution in the world because it essentially involves generating extra typing rules to make this one particular situation work. But it does work. You know, for every instance that you write, like you could have another instance for int. You would also generate a corresponding typing rule for appendisoc applied to a dictionary type verified semigroup int. And similarly for any other instances that you write. So, like I said, I'm not super satisfied with this solution, but it does do the job and it does avoid the issues that I mentioned earlier. So to wrap it up, I've been poking around, seeing what things work, what things don't work, and I found something that seems like it might work. I need to flesh it out a bit and try to make it a bit more formal and nice to look at, but I think the idea is there and it could hopefully be wrapped up and polished some more. So that's all I've got, so thanks for watching.
5 minutes for questions.
Yeah.
Switch the status.
Do you have a question?
Yeah, so you gave one reason why this append won't work. you say that there's another reason, which is that it's not even what you want to mean, like even if it, like, if you back up one, yeah, like here, what that would mean is something like, I mean, it doesn't even type check.
Right.
Right, because D could be any verified, like if I'm a verified semi-group, I only promise that I'm verified. I'm not promising anyone else is verified, right? So like what you wrote there would suggest that you give me any D and I promise that it will be verified and under my X and Y's and Z's and I don't want to promise that, right? So it's not just about expressiveness, it just means the wrong thing, no?
I think so, yes. I only went down this route because, like I said, I was pursuing a solution where we wouldn't have to hack in any extra typing rules or things of this nature. So I was really eager to try this because I thought this would just take care of everything in one fell swoop. But unfortunately, life is never that easy. And yeah, that just doesn't seem like it's a tenable approach at all for at least a couple of reasons, as you noted. Yeah.
Don't you have semi-group superclass in scope? Can you use that?
Mm-hmm.
Yeah.
Can you say that again?
Semi-group superclass is of type semi-group B,
Right.
which I'm assuming is equivalent to D.
Almost, but not quite. Oh, I see what you're saying. You're saying, can I grab the implementation of a pen from semigroup? Yeah, I suppose, but I think that only works in this particular scenario because, like, I have deliberately included semigroup as a superclass here. Like, if I had actually inlined this append method into the class itself and had no superclass, then I think we'd be back to square one because we wouldn't be able to just grab it from that dictionary. But and you seem like you've had a revelation of some sort.
But then you would just grab that, right? Instead of, like here we're saying, use in the type for append and solve, use semigroup superclass in the dependent cell. So if semigroup superclass were not that, but just append, then in the type of append and solve, use append. Right? So, but you need some kind of dependent somewhere or other.
Instead of append dx, it would be append semigroup superclass x.
Or just my append, like suppose you.
Right, I think what and you're saying is like, you know, even if we got rid of the superclass and inlined append into it, then you should be able to refer to it in this refinement type, which I want to agree with you, but I feel like there would be some technical complications because, you know, like I said, in GSD core, the only way you can actually type check any uses of append is by grabbing it from some dictionary. Like, it's just not going to work otherwise. And I think that's really the critical bit here is that we don't have a dictionary to grab onto in that scenario. So it's difficult to imagine how all the details would work out. Maybe I'm wrong though. There might be some way you could wrap it all up and make it work. Yeah, it's you need some like self pointer and that feels a bit too much like C++ in my case. So I didn't explore that.
You don't have to call it this.
Okay, this. We can bike shed the names, I guess.
I'm not sure what you're saying the next slide. I'm not sure what this is.
So this is a recap of a conversation I had with Ranjit Jalla, where he explained why that approach would work. So I understand it up to the point that Liquid Haskell does not have the ability to express types like this because Liquid Haskell does not have the ability to express types like this. That was the more detailed reason he gave. So
can you write a rank 2 type and define it?
can I write a rank 2 type? I don't know the answer to that question.
I'm not sure what this is.
I want to say you can, but I feel like it's only because there's lots of trickery they pull with uninterpreted functions and stuff. Like, I'd have to get back to you on that because I honestly don't know. All right. Oh, sorry.
Even if you could use for wouldn't that be wrong? Because you don't want it to work for all dictionaries, you just want it to work for one specific dictionary.
Yeah, not just one specific dictionary, but like this particular dictionary they're writing instance for. And like that's what I think Ken was getting at with his comment about self for this. Like we need some way to refer to the actual thing that you're declaring here. And Haskell doesn't really have or rather liquid Haskell doesn't really have a convenient way of talking about this at the moment.
All right, thanks.
Cool. So this semester I've been kind of trying to add implicit arguments to the language Pi, developed by Dan Friedman, who's right here, David. David and Dan. My coursework has just been kind of swimming in dependent types using Pi in one class and Agda in another. And there's a lot of things you can do in Agda that are really nice and really quick, but I would not understand the implementation looking at it. And Pi is this, just very pure, very elegant implementation of the type theory. But it would be nice to have a little bit more of a bell and or whistle. And so, right, without betraying that simplicity, can we get just a little more smartness? The motivation being, so this was a proof from our homework due tonight. And we're trying to, right, just append and map on vectors. And we have tons of these arguments that get, shown over and over again. And if I was trying to show this to someone who didn't know about dependent types, they would have no idea what this is doing. Focusing, okay, this Y is probably really important. It's kind of not. This would be a lot nicer, right? Where we just see, okay, we're mapping F on the front, and then we're appending those two vectors. That'd be nice. And my model here has been to kind of try to make it look like Agda. And so that's basically what this would be the signature in Agda, and it kind of is pretty much the same. We're not going to get rid of the arguments, but we'll just get rid of them in the usage of their functions. So I'll get into some of the rules that kind of talk about this, but just for those of us who aren't really familiar with the methodology in Pi. So we're using a bidirectional type checker, and there's 4 kind of fundamental judgments that we make. That something is a type, which will be written like this, that 2 things are the same type, which I'm not going to talk about, so you don't need to worry how to write it. That some given value inhabits a given type, and maybe Dan even has something to clarify this. I think of, so the epsilon there, that's in check mode, and so if we want to assert that x is an x, we'll use that top rule. And if we want to say, hey, I don't know what this inhabits, can you tell me? We'll use synth, and then we'll get back that type. And so those 2, I think, are associated to that judgment.
So epsilon and synth are the things you swap out depending on whether you're checking or synth mode?
Exactly.
Okay.
Yes. And then synth will, right, check will just give back this x naught, which is the value after normalization and maybe a little elaboration. And then synth will say v, type x, and then that same value. And then this, and then this last rule that x and y are the same type. In normal Pi, that's just nice simple alpha equivalence. And to do the implicit typing, I kind of had to add unification. And so there's a new relation that x unifies with these 2 things, some type y, and some set of values v's, where if you plug in v's into x, you'll get that type y. And this is, the first thing that was actually something I thought of. So if it's a weird way to say it, would love to hear that. But this is what I'm going with. So these
This one has no gamma at all?
So to write alpha equivalence doesn't need a gamma, and so unification doesn't need a gamma. So we'll start with kind of the basic part of unify. So right, it's just alpha equivalence, totally what you'd expect, plus this one rule where if I'm looking at one of these pi I types, this is the new form where I want x to be some implicit argument of type A, that if I know that the inner of type B, when I substitute x out with v, unifies with t and some slightly smaller set of implicit values, that then the pi I, we add that value to the set of implicit arguments, and it all checks out.
Sorry, what is v and x? They're both variables, or
So,
one is
sorry, no, this is, yeah, no, thank you. So x is a variable and v is a value, a term.
So the notation in the upper left corner, does that mean substitute what for what in what?
It means
V for x.
v for x in v.
Do we need to track v is an A?
Yes. Yes, okay, great.
What was that?
That v better be an a. Yeah, sorry.
But then the environment is actually just a list of terms.
So the v colon v is. So that's not an environment. What that is the values that I needed to kind of instantiate this pi I to be type t. So it was basically, I'm going to go to this unify relation and say, find me the values such that b and t unify without any weirdness. And there are going to be some variables that you need to find values for to make that happen. And so basically on the right-hand side of unify is that final type that worked and the values that were found in the process.
Can you see what pi I x a means?
It means, so that's, I guess, yeah. So the normal expression in pi is just, without the I, pi xab, and that's a dependent function. And now pi I is just, I'm a dependent function where you don't have to give me the value of x, or x
I
is implicit.
is not a number. I is just a letter I.
Pi I is the.
It's a new form, yes.
Implicit.
I should have made that more clear.
Well, it's implicit.
It isn't. Yeah. Okay. Any other problems with this rule? I hope it's okay. Okay. And so the way, like this is, there's a couple other rules to deal with application things when we unify, but this rule shows up just at the end of our check mode. So we have a lot of forms that we want to check against a type, and there are certain forms like application, like all elimination forms that we just go to synth to deal with. And so in our else case of check, it says, okay, this wasn't a form I want to check, so I'm going to synthesize a type, and then compare that type against the type that synth gave me. And so the case that the arrow is pointing to is the one I added. Before it was just use the alpha equivalence function, same type, to say, are these the same? If so, I don't care about what it returned, I'm just going to keep going. And now it's basically, okay, do I need to do my unification? Do I need to hop to miniKanren? If so, do that instead. Any questions about that? So then just a couple other just simple rules. If I want to say blank is a pi I, here's the rule that talks about it. Right? If A and B are types, then pi I xab is a type. And that this new form lambda I, which is a lambda of no arguments, is a pi I if when we add x as a to the environment, we can get out.
So is lambda I something that the programmer writes explicitly, or is this just something that appears after, like, desugaring?
No, so as of now, it is something you have to write explicitly, which first thing I want to get rid of.
Gotcha.
But where I am now, you do have to write it.
Okay.
Just because, since pi I is this special type, it's not, like, if I'm thinking about Agda, like, the for all isn't a type, as far as I'm concerned. Or as far as I understand it, I guess. It's a way to introduce variables that's not necessarily a type. Pi I is still a type, and so types have to have a constructor, and so you construct a pi I with a lambda I, which I don't like, but that's what it is right now.
Okay. So I guess in the current state of things, is the only implicit thing that you can apply things of type pi I to something else without having to explicitly give the arguments for the things that unify
Yeah.
the implicit arguments?
Yeah.
Okay.
And
And
it's interesting.
there's not like a different syntax for all this, just part of how function application works.
Yeah.
Okay.
Yes. So just, right, to go way back, it's just, when I have vec app and vec map that are normal pi's, all of these are given, right? This is a different function, but you can just get rid of some of those things. So if f takes atoms to nats, I don't have to tell it atom nat. If front has length 12, I don't have to tell it 12. Those are the types of things I was trying to target. That's what. And now, so kind of the first real interesting rule. So when we want to do application on a function that is a pi I, right, so I have this f of arg, I can get the type of arg, and I find out that, f is a pi I. What I do is basically try to unify this pi I type with some pi type, where that pi type accepts what arg was, and gives me this tau I, which was the inferred type, kind of given as a miniKanren variable at first. And then it comes out, as well as all of these arguments, because there might be more pi i's within V, and we just kind of find them all for this first kind of layer. And we give those back, and then we can kind of say, okay, I'm going to shove in all those arguments I just found before doing the one you gave me, and we'll move forward. And then here's basically the same rule, but for application on more than one argument, should be fairly the same. Any problems with this? Any typos I made? Okay. And then where these show up is obviously in synth mode, because that's where we're going to deal with application. And so if we see an application, we kind of move to this solve app function. And right, this hopefully looks fairly similar to the rule, where I'm going to run my solve arg, which for some pi I type, and some a that I needed to make sure tres accepts, I'm going to get back that tau I type. Tres is the same as tau I here. And then just shove all those arguments I just found in before the actual argument that was given. And now I can show just a little bit of what it looks like. And again, I really dislike the fact that you have to write out lambda i's. Right. So here's foo, which is our normal vet cons, and it has this implicit type for the vector, a value of that type, an implicit length of that vector, and then the vector itself, and I'll get back one more. Like, it's not pretty, and I really do want to get rid of this. And the state right now is that you have to kind of stagger the pi i's so that you don't have implicit arguments that aren't relevant to the real argument you're being given. So when I move this nat, this n, above the x, it still could be anything when we're looking at x. And so you have to kind of stagger them, which I'm hoping to kind of fix, but that's where it is right now. And then we have kind of, back map with a little bit more involved and a little more defined, and a lot more lambda i's you have to write out. And it all checks out. So that's where it's at right now. Right. Some things I want to still do, get rid of this lambda I. I haven't made the match cases for equal types and a lot of complicated things, so I want to do that. I would enjoy adding a heuristic to make it smarter. Right, the typo in one of my types where I didn't check that the value I found was an A. It would be nice to get it like Agda where it's really just a for all, and my inferencer will find the type and then confirm it. Some of you know this, some of you don't. I'm starting grad school myself next semester, and this was my first kind of big open-ended project where I had to kind of just figure out stuff on my own. And it was really humbling to kind of realize what the process is like. And these are just some questions I would love to ask, and if you have an obvious response as to how you kind of deal with, when your initial idea doesn't seem right, how long you wait until you go look for papers for ideas, the questions that are all stated here. Interested to hear some advice or some tactics that anyone has developed in these kind of areas. If not,
So let's thank Ben first. Why don't we do 5 minutes of high questions, and then we can do 5 minutes of this. All right, go ahead.
I was thinking about your miniKanren queries. Do you only care about succeed or fail, or do you keep the substitution?
it's basically just succeed or fail.
Okay. Is that possible that you have two different pi I in two different places, but that may conflict with each other?
So, if I understand your question, I don't think so. So, do you mean a pi I that's kind of further in?
Yeah, like for this pi I, you unify with some type, and you have, say, a substitution or a list of answers. And somehow, if you run this pi I in other place, you might get a conflicting answers in that place.
So part of what I'm still dealing with is making sure that in other contexts it works right.
Yeah.
And so that's just what I'm hashing out.
Okay.
So as of now, it's been in a simple environment, and so it's fine. Yeah, no, that's absolutely an issue that I'm trying to deal with.
I'm kind of curious to know what the state of error messages are for the system at the moment.
Yeah, sure.
You gave one slide. Is that currently the only kind of error message that results when things fail to unify? Or are there other situations in which implicits can fail? And if so, like, what kind of things might it tell you?
So right now, so you know, I mean, there's plenty of errors. Like if I what do I want to do here? We can make a yeah. So it'll do the things you expect. Right? Yeah. Okay. So this isn't. This thing needs to be a function. If we do something like if I do something like this. Right, this will say on functions like that is on I, which is and if I, you know, do something like that, I mean, give me the expected error.
Okay.
I can, if you want to kind of gross
Yeah,
error.
I guess what I was thinking more of is not really so much as defining these, but rather applying a function that takes an implicit argument somewhere and unification failing to discover something that unifies with it. Like, I'm trying to think like a really silly example, like, you know, something which takes one implicit argument and always returns a net. And like, you know, where the implicit argument might be ambiguous if you try to apply that function somewhere.
Like where it's an implicit argument that doesn't matter.
Right, yeah, something like this. So like, if you were to change both of those to nets,
Yeah.
and you were to apply this somewhere, then would it complain that it doesn't know what to unify x with? Or
So
does
now-
it just work?
Yeah. So right, here's didn't matter what that was, and that's. I'm glad you caught that. Or I guess impressed you caught that. Yeah, right. That's.
Yeah, it's always tricky trying to figure out how to format error messages involving unification variables. Like,
Yeah.
if there was a good way to do this, I wish I knew it.
Yeah.
I'm not aware of one.
So, not everything can be turned into an implicit for all, right?
Right.
So, when can you turn something into an implicit for all?
Yeah. So when you have an argument that will exactly clarify what the other one should be, then you put all the implicit ones first, and then that argument. That's kind of when it will work. What I was really going for were these vector list, very, very simple, very obvious arguments that I didn't want to write. Once I expand to handle more things, it'll be more interesting. And hopefully I can start.
If you do something which cannot be inferred, then what happens?
So it'll time out and say good enough.
Okay. If you try to unify for a certain number of seconds and if it can't do that, then you just give up.
All right, that's it. Thanks for your talk on Pi. Okay, so these are very, very broad questions, and we could go on forever, but I challenge people, if they have something to say, let's try and keep it 30 seconds each. And we can spend a couple of seconds thinking about it.
4 and 5, get things done. Getting things done.
And so maybe what is getting things done?
Google it.
So that's a name of the system.
Okay,
Of a specific thing.
I'll look it up. Get things done. I mean, that works. That really should sum all these up pretty quick.
I'll take number 1 for $50.
I don't have $50.
And that's not an answer. Have real users.
Yeah, Jeremy has kind of been guiding me. I was talking to him and was trying to deal with some form, and he just said, no one's ever going to try to write that. Why do you want that to work? And I was like, oh, right. Yes, have your users. That's good.
I missed that one. I need to hear it. I know it cost me money, but so. Your answer was?
Just that Jeremy said to me a similar thing.
Oh.
You know, if I was trying to directly apply a the statement with a pi I on it, and it was just, no one is going to write that. So it's really okay if you can't handle it.
So for number 3, how long before you start looking for papers? I think you look for papers first.
Okay, yeah.
Because you need to understand what everyone else is doing to situate your research in the context of all of it. If you're sort of off on your own, then no one else will understand what you're doing.
Yeah. I've read this happening at the start, yeah.
So, add to what he said. Daniel likes to tell me to not actually read the papers, just look at them. Don't read them. Just look at them.
I think I have a definition for look at them, which is you read the abstract, you read the conclusion, and if you're not bored after that, then you can start reading it. And you do read it, you don't read any of the proofs or any of the theorems. You read the theorems, but not the proofs. And then you can start finding which ones that you might be looking for inside it. And that didn't come from me. That came from my major professor, Terence W. Pratt. But, he said that's how he does research. He says, because there's tons of papers. Now this was before the internet, I should know. So the word tons is taken on a totally different meaning. So anyway, that's I actually have a quote that I like a lot. That is my quote. And it may not make you better at research, but it might help. And that is, I kind of don't care whether or not someone else has solved a particular problem. I care how I would solve the problem. And if it turns out to be that someone else has already done it, well, that's fine. And you find that out. But you often walk into a problem with some sort of vague notions, not really ready to tackle that particular problem. And so I don't bother worrying about whether or not someone has solved it. I've been working on something, I need to do it. A good case in point was convincing my co-authors that we had to get rid of using names for variables in what's now called miniKanren, because you couldn't make the statement that the argument order didn't matter. Right? Because you would be able to tell, oh, well, that one had an X and this one had a Y as its name. Because you're only going to get one anyway. So the reification thing came about because I just wanted to be able to say X equals Y, X is unified with Y is the same as Y unified with X. Now, I don't know if anyone ever bothered to think about it or not. All I know is when I was looking a little bit at it for a while, very little of it, I see these giant long names that look like one of cancer, whatever's very long Jensens that you never want to see. And I thought, well, I don't want to see that. But those were in the books. You know, those Jensens were in the book. And I kind of had a negative feeling about that. So the combination of those two things led to coming up with reification as a way to attack lots of other problems. But you never know. You really don't know. Just plow ahead and see where you land. And then look.
All right, we're going to do one more. I think Ken really wants to say something.
Oh, I'll let someone else.
All right. Yeah, okay, Ken, you can rest.
I don't know if Dan's going to agree with this, but let me generalize what you said to a recursive, you like it, procedure, which is also about reading and writing, which is when we write, we try to put a punchline first, like in the title or abstract and conclusion. And so when we read, we want to read the punchline and figure out how we would achieve the same punchline then maybe match up what we do with what they do. And this again can be done recursively. Like, oh, I want to prove it the way they did, but they have lemmas. How would I prove those lemmas or whatever? So, and that's not just how to do research, it's also how to understand better what other people did.
Thanks, everyone.